So the sheet will come back to you? Okay. Yep. All right. So that is that. One other thing. This coming Thursday, I cannot be here, so Sandy is going to cover. It's just the retake day. The first part of that class will be just you guys working in your groups and preparing however you wish. The exam isn't going to take the whole period, so there'll be like the review part in the beginning. Feel free to ask Sandy questions if you have any last-minute questions. But again, we ask that you prepare if you're going to come in and do one of these makeup exams. That's the coming Thursday. I won't be here. Sandy will. A week from today is our final class. It's the final Tuesday, Thursday of the semester. And on that day, it's just our review day for the final exam. It's going to be like the other review days where you guys will work in groups on whatever you want to work on. So nothing really together, all of us working on the same problem. The final exam is coming up. Our official time is Thursday the 15th, which is a week from this coming Thursday. Not a bad idea to put that in your calendar right now if you haven't already. Our exam is from 10:30 to 12:30, which is a little bit strange since our class meets at 9:30. Exam does not start at 9:30. It's 10:30 to 12:30 on that Thursday. Now, we have the same policy that we had all semester about you guys being able to take the exam with any of the 5 sections. Our day is this Thursday, and unless you tell me otherwise, I'm going to assume that you're coming here on Thursday, 10:30. If you wish, you can take the test on Tuesday with Sandy's class. Notice that there is a nice thing that it gives you 5 extra days to study, which is not insignificant. Here's the problem. Suppose you plan on taking it here on this Tuesday, and then some emergency comes up, you get a flat tire, you can't get here, all of a sudden you have a 0 on the final exam. That's a real problem. If you plan to take it on Thursday and some emergency happens, you still have time to take it again. But if you plan on taking it Tuesday, you better make 100% sure you can be here on Tuesday. You don't take it by that day, you didn't take it. There are a couple of other options on the Monday, Wednesday, Friday class. All sections are in this classroom. You could take it on Friday the 16th, you could take it Monday the 19th. There are a lot of days you could take this thing. If you know you want to take it at any time other than our time, our normally scheduled time, then you got to let me know. Again, we want to make sure we have enough copies for everybody who's going to show up. Is there anybody at this moment who knows they don't want to take it on this Thursday and would like to take it in a different time? Okay, that's fine. If you decide you're not taking it at the regular time, you got to let me know before or by the last class, which is a week from today. Okay? So make sure you tell me. Otherwise, I'm assuming you're coming at the regular time right here. All right, so I think that's all the logistical stuff. Maybe one more thing. So let's open the blue to the last section of new material, which starts right here on page 272. Okay, where's the makeup sheet? Thank you. Okay, everybody got it? Everybody has all the info they need? Great. Okay, so on page 272, there's the usual thing about resources you have available during the final exam. I just want to highlight that in the QEF3, the yellow 3, there is a practice final exam, and there are even more practice problems in there. Additionally, in blue, there is a practice final exam. So lots of resources for you. One other note is that the Math Studio coverage changes. All semester it has been dictated by this yellow piece of paper. This goes through the last day of the semester, which is Wednesday next week. Starting on Thursday, the schedule will change. I will post tomorrow an updated one. So you'll see a different color piece of paper that will guide you for when people are going to be covering the Math Studio next week. All right, any questions on any of that logistical stuff before we jump in? Okay, so let's take a look at here on page 273. We'll go to Julia for the objective. Good, Jessica, number 1. Okay, so you got two numbers that you're going to be typing in right now on your calculator. If you don't have one, you'll have to just sit tight for a moment. But type each of those two numbers in and just hit enter. And then let's talk about what the calculator says when you hit enter. Okay, so we're discovering some calculators can't handle the number that's that big. Other calculators don't do anything. You hit equals and it just sits there. Some calculators, however, change the number. And they write this funny thing, 6.022E23. That right there is not quite scientific notation, which is the topic for today. It's like the calculator version of scientific notation. Here's what it means. It means that this number right here is exactly the same as 6.022 times 10 to the 23. I'll pull the calculator up again. 6.022 times 10 to the 23rd power. That thing we've just written in blue is called scientific notation. Turns out that there are plenty of numbers that scientists and other folks have to use that are really big, and it's quite annoying to have to write this number with 20 zeros, and it's probably even more annoying to have to read it, because then you have to be really careful as you count how many zeros are there. So scientists have come up with this compact notation to say exactly the same thing. 6.022 times 10 to the 23rd. I'm hoping we believe that these two numbers are equal, not just because the calculator says this, but what happens to a number if you multiply it by 10? Like 5.8 times 10. You move the decimal place, one spot over, right? 5.8 times 10 is 58. If you multiply by another 10, you move the decimal place over again. So we're multiplying by 10 to the 23rd. So how many times are we moving that decimal point over? 23 times. So let's imagine moving that decimal point over 23 times. There's the first move. Second, third puts me here. But I'm supposed to move 23 times and I've run out of numbers. So what are the invisible numbers that we're about to bring in? All zeros, right? You could have a bunch of zeros there without changing anything. I made 3 movements there. How many movements are left over? 20, right? Because we had 23 movements to start. So 20 zeros will get me exactly this number over here. And it sure was a lot easier to write this thing in blue than it was to write the original thing that was on your paper. And it's also easier to read, 6.022 times 10 to the 23rd. So the E, where did this E come from? E stands for exponent. And we're just telling you the exponent. And it's always the number 10 because everything we do calculation-wise is base 10. All of our numbers are based on the number 10. And so we don't need to include the 10 here as long as we understand it's always times 10. Okay, so that is that guy. And then did anybody type in this bottom number here with the zeros in the front? What did that one say, Meg? It said, say it again? Yeah. Good. And when Meg said E, negative 11, I'm translating that to 10 to the negative 11. Okay, let's see if we buy this. Multiplying by 10 moves the decimal point one place to the right. We saw that already. You guys know that 10 to the negative 1, what do we do with that negative exponent? We put it downstairs, so it really becomes 1 over 10 to the positive 1. Yes? So if you see 10 to the negative 1, it's really divide by 10. That's what the instructions are. So if multiplying by 10 moves the decimal point one place to the right, and dividing by 10 sure feels like it's going to move the decimal point one place to the left. So let's see if we agree with this version of the number. Apparently we're supposed to move the decimal point here. How many places in which way? 11 to the left. I'm going to move it once here. I've run out of digits. So what are the invisible numbers that we bring in? Zeros. How many more movements do we have to do? 10 of them, because we were moving 11 times and we only did 1 so far. So 10 zeros in the front, which lo and behold is exactly how many zeros we had there. Okay, so we'll just put arrows here so these guys are equal. And here's what we'll say. How do we know whether or not a number is in scientific notation? Well, looking at just this piece of the number, the 6.022, 6.742, I will say that that number is definitely between 1 and 10. You guys agree both of these 6 points are between 1 and 10? And any number that you're going to write in scientific notation has to be between 1 and 10. Said another way, what you want to make sure you do when you go to scientific notation is put the decimal point, let's get this out of the way, is put the decimal point just to the right of the very first non-zero digit. So 6 point something, 6 point something. You move it just to the right of the first non-zero number. That's how you decide that it's in scientific notation. Two other observations here. First one, this number right here, this 6022 with lots of zeros, is definitely bigger than 1. What about the bottom number? Definitely smaller than 1. And it turns out that's the cutoff that dictates what kind of exponent you're going to have. If you have a number bigger than 1, what kind of exponent landed up on the 10? Positive. If you have a big number, it's going to have a positive exponent on the 10. 100, 1,000, 10 million, all these big numbers, all positive exponents on the 10. But if you are smaller than 1, then you end up with a negative exponent on the 10. Okay, so I think that's it. I guess we can fill in the blank here. The exponent on the 10, I said here was positive, and here was negative. So big numbers, positive exponent, small numbers, negative exponent. The 1 is a special case because it's the cutoff. I guess if we're wanting to fill everything in, we would say this guy is equal to 1. It's not bigger or smaller, it's equal. And if I'm going to write it in scientific notation, which nobody would, but we can, then we write it as 1 times 10 to what power? It's 0. Yeah, I can't put anything up here other than 0. And we saw last time that anything to the 0 is how much? Is 1. And so, what's that? Yeah, just 1 times 1, or 1. And you can see that that 0 is exactly between the positive exponents from the big numbers and the negative exponents from the small numbers. 0 is the only one that isn't positive or negative. Okay, 2 asks if anybody recognizes either of these numbers. I expect some of you have seen this 6.022 times 10 to the 23rd. I'd be surprised if anybody's seen the other one. Anybody recognize either one? Well, we did just use them. The one on the right, yeah, I guess it does have a bit to do with acceleration. But like outside of math class, have you seen either of those numbers? Anybody taken chemistry before? The left one is called Avogadro's number. You heard of that? I don't fully understand it myself. It's the number of molecules of a certain substance in 1 mole of that substance. The problem is I don't know how much a mole of anything is, but anyway, it's just counting how many of these really tiny things are in this collection of molecules. And it turns out it's just this universal constant, regardless of what the substance is. Like we can change the chemical, but it's still that many molecules of the chemical in a mole of that chemical. And so that's Avogadro's number. Just make a mention of that. I'm not 100% on the spelling. Are there 2 Ds? I don't know. Avogadro's number is that guy. And then this one right here is called the universal gravitational constant. So is this something you guys have heard before? every two objects in the universe exert a force on each other, like they're pulling each other towards each other. And for us, even though like Julie and I are exerting a force on each other, our masses are so tiny compared to the mass of the Earth, which is exerting a much stronger force on us, that we don't actually feel the force between all of us. But everywhere in the universe, objects are pulling towards each other. And it turns out that this magical number is a constant which is part of the formula that tells you exactly how strong the force is between two objects, between Julie and I, between our sun and some star millions of light years away. That same magic number pops up in all of the force calculations. Anyway, I include these two numbers just to show you that scientific notation makes really important numbers easier to handle. Okay, let's try this table together here. All right, so the first number is in what we call decimal form, an ordinary looking number in scientific notation. First thing we need to do, this is a non-calculator thing. Now we're going to figure this out because we're going to be doing this on the test. Okay, we need to write this as some number that's between 1 and 10. So where are we moving the decimal point to? Next to the 9, before the 9 or after the 9? It's to the right of the 9. You guys buy that? It's got to be 9.007. You keep moving that decimal point until it's exactly one place to the right of the first non-zero digit, times 10 to some power, and then we count. So 1, 2, 3, 4 lands me there. Is that right? 5. I have to move to the other side of the 9, so it's a 5. You guys okay counting the number of movements? Don't count zeros. Counting zeros is not reliable. You need to count how many times you move that decimal point. And then the last question, should it be positive 5 or negative 5? I heard one vote for each. Positive 5 or negative 5? A few more votes. So here's how I decide which one it is. You could memorize, oh, if you move the decimal point to the right, then it's blah. And if you move to the left, then it's blah. I would not memorize that. I would look up here and understand that big numbers have positive exponents. And numbers very close to zero, small numbers, have negative exponents. That's what I would understand. So is that a big number or a number that is small? It's quite small. So what kind of exponent? Negative. So that's our answer there. Okay, moving on to the next one. Somebody we haven't heard from yet. What's going to be the first part of this when we move it to scientific notation? 2.789. Folks okay with that? We need that first number to be between 1 and 10. That's the only way to make it happen. Times 10 to some power. So this is not about counting zeros. It's about counting movement. How many places do we need to move the decimal point from its current position to the new position? How many? One vote for 11. Other votes? How many spaces do we need to move that decimal point to get it to land at 2.78? I heard another 11. Is that all right? So feel free to count one at a time. If the number is broken up with commas, then you can count 3 at a time for the beginning, right? 3, 6, 9, 10, 11. So I'm going to throw an 11 up here. And then the last thing we need to decide, positive or negative exponent. What kind of number is the original? Big or small? Big. What kind of exponent? Positive. Everybody okay with the decision-making process here? Okay, so that's going from decimal form, like normal looking numbers, over to scientific notation. I also need you to be able to go the other direction. So currently we have 2.03 times 10 to the 6th. 2.03 times 10 to the 6th. So looking at that exponent, what kind of a number do you see? The exponent is positive, which means the real number when we're all done is going to be big or small? Big. So we have to make this 2.03 something big. Would you rather move the decimal point right or left to make it big? Move it to the right. Again, you're welcome to memorize stuff. the exponent's positive, you move to the right. If it's negative, you move left. But I think it's so easy. Like if you memorize wrong, you're going the wrong direction. So we move the decimal point 6 places to the right. And be very careful as you count. So it used to be here. 1, 2 lands me at the end of the first part. How many more spaces do we need to move? 4 more, which means we need to bring in what? 4 zeros. 1, 2, 3, 4. We don't need to put the decimal point there, but I will just to show that it's moved 6 places. And then finally, we'll be friendly to the reader and put commas every 3. So that number is 2,030,000. Last one here, 3.7 times 10 to the negative 4. Going through the same process. Exponent is negative. So the whole number is going to be small. Would you rather move the decimal point right or left to make this a small number? Let's move it to the left. So I'm going to write the 3 and the 7. And then start moving that decimal point. It used to be here. We're supposed to go 4 places to the left. I run out of numbers after 1. So 3 zeros in the front. 1, 2, 3. Here you must put the decimal point. So 0.00037. Questions on that? Easy, hard? What is this? Straightforward with practice, right? Okay. Next page is going to ask us to just think about exponents a little bit. Let's go to Meg K. Can you read number 4? Okay, talk with your neighbors for a few moments. You're going to write some number down in scientific notation with that positive or negative exponent. Okay, show of hands if you think it's a positive exponent. If you think it's a negative exponent, super. Positive because it's going to be a big number. 300 feet, 400 feet, I don't know, it's bigger than 1, right? 1 is our cutoff, so this one is positive. Okay, finally number 5, compute and simplify and then write your answer in scientific notation. Okay, this is a non-calculator question. So one thing you might be tempted to do would be to take these numbers, which are currently in scientific notation, and write them in standard notation or decimal notation, whatever it's called. The issue with that is you end up with some number on the top, like 0.0036, and it's getting divided by 300. And that's not a real friendly calculation to do. It's not the end of the world to do that calculation. But it turns out if you keep things in scientific notation and just practice a little bit, you can do these calculations really quickly. So let's give this a shot. Equals. Okay, first thing I'm going to handle is that negative exponent. That 10 to the negative 4. Where does it go? It goes downstairs. We've seen many times now negative exponents move. So I'm going to copy the 36 upstairs. I'm going to copy the 3 times downstairs. The 10 squared stays downstairs. But that negative exponent moves and becomes 10 to the 4. Okay. This is equal to 36 divided by 3 times 10 to the. Yeah, imagine, I mean, it's either 8 or 6. There's going to be an exponent on the 10 that we're about to put. You've got to do something with the 2 and the 4. Is it 8 or 6? I'll vote for 6. Imagine the 10s. I'm not judging. I'm just tabulating. Imagine the 10s written out. 10, 10, 10, 10, 10, 10. What is it? 10 to the 6. Apples and oranges come into play if we're adding and subtracting. But this is all multiplication and division, so it's fair game to reduce. 36 and 3. What do they become? 12 and 1. That's it. Right? We can just straight cancel because it's all multiplication. Okay, so this is equal to 12 divided by 10 to the 6. Can we reduce the 12 and the 6? 12 and 6. Cancel them, make a 2 and a 1. That 6 is what kind of a thing? Exponent. It's not going anywhere. I mean, it has nothing to do with the 12. How about the 12 and the 10 though? Because they're both big. And 12 and 10 can cancel and make 6 and 5. Is it okay to cancel the 12 and the 10? Why not? Yeah, there is an order of operations here. We know that exponents come before division, so that's one part. Is that 10 really just a plain 10? That's 6 tens all collected together. If you slash the 10 and make it a 5, then you have slashed all 6 of those 10s, and that's not okay. So we can't reduce this at all. What we can do is actually just write this as a decimal. If you take a number and divide by 10 to the 6th, you're making it big or small? Divide by 10 to the 6th? Makes it quite small, right? Multiplying by 10 to the 6th makes it big, but here we're dividing. Take that number and divide it by 1,000,000. It's going to be really close to 0. So let's take that decimal point, which is currently here, and move it which way? To the left. How many places? 6 places. So carefully move that guy 6 to the left. So I'll write my 12 here. That was 2 movements. How many zeros are we bringing in? 4. 1, 2, 3, 4. Put the decimal point. Last part of this problem says write your answer in scientific notation. It is not currently in scientific notation. So in some sense, it's going to feel like we're going backwards now, but this guy equals, what's the first part of this number going to be in scientific notation? 1.2 times 10 to the something. Is it 4? Yeah, we just have to count carefully. 5, is that all right? Getting that decimal point to move between the 1 and the 2. 5 there. And the only last decision to make, is it positive 5 or negative 5? Negative because, Jen, it's a small number. So that's our answer. Any questions? Okay. So there are some notes that you can take a look at later, but for right now, jump in on the classwork. I'll put the flags out and answer any questions if I can.